Hi, I'm Ian Smith. I'm a postdoctoral researcher in the Human Performance Lab at the University of Calgary, supervised by Dr. Walter Herzog. I've been in this position since April 2014. I guess that means I've been here for a year and a half, and I've got funding for another 2 years of this, so lots of great experiments to come.
Okay.
Ian, nice to get you for the interview. And how long have you been studying here?
About a year and a half.
A year and a half?
Yeah, since April 2014.
Okay, and what did you do before?
I was doing a PhD at the University of Waterloo. That was in muscle physiology.
And what's your current study about?
I'm looking at structural and functional aspects of muscle contraction, history dependence, fatigue, ultimately how that relates to the way muscle works in both normal and diseased circumstances.
What are you doing exactly over here?
Okay, so this is from the day that you were that you can visit. Okay, so this is a skin fiber apparatus. I've got a force transducer here that measures the force, a length controller here, essentially a motor that controls the length. We can either shorten or lengthen the muscle or keep it at a constant length for an isometric contraction.
Okay.
So what I was doing with this is seeing how changing the basal calcium concentration can affect the rate of force production. Yeah. So the other day I was seeing how changing the basal cytosolic calcium concentration can affect the rate of force production when a muscle is activated. So that's fairly preliminary data, just showing in principle that essentially if you change the saturation of the calcium buffers at the onset of contraction, you can get a faster rate of force production if you've got them with more calcium at the onset of contraction rather than completely unsaturated.
And is there any practical application afterwards?
I think there is. It might be species dependent though.
Species dependent?
Yeah.
Okay.
Yeah. I think if there is a physiological effect, it's more likely to appear in muscles that have a lot of parvalbumin present. That's a calcium binding protein that's present in small animals, mice, frogs, things like that. And so the reason that I'm thinking that is after tetanic contractions in mice, there's an elevated calcium concentration afterwards that doesn't seem to be present in muscles that don't have parvalbumin present. So at the same time as these events happen, we've got increased rates of force production that we can't explain otherwise. So it's the investigation of a hypothesis, and we'll see where it goes from there. Essentially how this works is we've got the permeable fiber in there, and we expose it to a series of different baths. And we do that with this little guy here. So each of the baths will have a different solution in it. We usually start with a resting solution. So there's a lot of EGTA present, no calcium at all, so the muscle's at rest. We'll flip it to another one. This one will usually be relaxing, or still a relaxing solution, but this one will have low or no EGTA present and also no calcium. So this washes out all the EGTA, and then from there we put it in a activating solution that would have a lot of calcium buffered with EGTA. So we've got high free calcium concentration, and that will cause the muscle to contract. So we let it contract and do some sort of experiment, whether isometric, isotonic. So once that experiment will be done, we bring it back to the relaxing solution, and Bob's your uncle.
To your current poster for presentation in?
So this is for the Canadian Society for Exercise Physiology.
So
I'm interested in how the basal cytosolic calcium concentration can affect subsequent contractions. Really the reason for this is during my PhD I found that there are increased rates of force production following tetanic contractions, which coincide with elevations in the basal cytosolic calcium concentration. And I wanted to see if there's any way that these could be causally related. So there's actually going to be a series of studies on this. This one's just a proof of principle. So I'm using rabbit psoas fibers, so skinned rabbit psoas fibers, and I was varying the concentration of calcium prior to inactivation. So this is a raw tracing showing the typical experimental protocol. So we start off with relaxed fiber, wash off the relaxing solution, incubated it in a pre-activation solution with varying amounts of calcium, all subactivation threshold, so no cross bridges present. Transferred to an activating solution with lots of calcium present, let force reach a plateau, and then relax it, and then do the whole thing again with a different pre-activation concentration. So there are really two possible mechanisms that would cause a change in the basal cytosolic calcium to affect the rate of force production. The first is a competition mechanism where calcium is actively buffered by different cellular constituents, and these can compete with calcium binding to troponin C. And if you increase the saturation level of these competitive calcium binders during a subsequent contraction, more calcium is going to be channeled towards troponin C, so you get faster thin filament activation and faster force production. So to investigate this hypothesis, the reactivation solution has a high concentration of EGTA, acting as kind of a stand-in for those cellular calcium binding proteins and molecules. And the second possible mechanism is one where having increased basal cytosolic calcium concentration can actually influence the contractile proteins themselves. So maybe calcium binds to the thick or thin filament, and that imparts some sort of structural change, which makes cross bridges more likely to form during a subsequent activation. So to see if this is actually occurring, I'm using pre-activation solutions with very low concentrations of EGTA, so they'll be completely overwhelmed upon activations, and there's not going to be any competition there.
Oh, okay.
Sections. This one's with 5 millimolar EGTA experiments, looking for a competition mechanism. So skin fiber preparations are notoriously unstable. So they're going to produce less force with each subsequent contraction. So to control for this, I ordered the experiments both from high to low and low to high pre-activation concentration to control for this this order effect.
Okay.
So we've got some raw tracings here. So both of these are going from a pre-activation solution, varying levels of calcium. It gets transferred through the air and then dropped into the activating solution. So regardless of whether the pre-activation solutions were ordered from high to low or low to high, the pre-activation solutions with low calcium had delayed force production and lower rates of force production upon activation. So we know something is going on here, but we can't say for certain whether or not it's actually the competition mechanism.
Okay.
So that's when the second experiments come in, where there were there was very low concentrations of EGA. So this is 0.15 millimolar. So this one I only did I only did 2 concentrations, one with no calcium and one with a PCA of 7.0. And again, I changed the order, so it started with calcium-free, then to PCA7, and then back to calcium-free. So if the one with higher calcium would have an effect, it should go up and then it should drop back down afterwards. So similarly over here, we go from a pre-activation solution, transfer it through the air, go to the activation solution. There's absolutely no discernible effect from the higher calcium.
Okay.
So if there is anything happening, it seems to be the result of competition for calcium binding with troponin C.
Interesting.
So, but again, this is EGTA. There's no EGTA present in intact muscle. So we need to do more experiments to see if something can actually be happening in intact muscle. But we do have proof of principle that there could be something there.
Any ideas now for your next study?
Going to be looking at two different approaches. One of them will be doing some computer modeling where we've got different molecules that can compete with troponins and bind calcium. So specifically parvalbumin and possibly ATP to see how changing the calcium saturation of these molecules affects the rate of force production and activation of the thin filament. So that's the computer component. And then another one, which is still very much in the idea phase, would be looking at intact fibers and actually directly injecting parvalbumin in to see if that decreases the rate of force production as compared to an injection of just the empty vehicle. So if you do get a decrease in the rate of force production, that would show that parvalbumin actually does directly compete with troponin C.
Interesting.